Today we're going to be looking at graphing the derivative of a function given just its graph, not its equation. So we know it's easy to just be given an equation like, for example, x squared, and know that its derivative is 2x. But what if you're just given the graph of f of x? How can you actually graph f prime of x? That's what we're going to take a look at today. There are many different cases that we're going to look at in total. Today we're going to look at graphing f prime giving f, but we are also going to investigate some other cases in some other videos. The last case we'll look at is, for example, given the second derivative graph the original function f. I want you to notice that when we look at case 2, graph f prime, graph f double prime given f prime is the same steps as going from f to f prime. And that's because each is just each other's derivatives. For example, f double prime is derivative of f prime, so it's going to be the same steps as graphing f prime given f. We're going to look at case 1 today. Graphing f prime given f, we are going to notice some things that we're going to use when graphing. We're going to be using increasing and decreasing because that has to do with the derivative. We're going to be using concavity. Believe it or not, concavity actually influences the derivative of the original graph. We're looking at inflection points, and we're going to be looking at relative min and max, among other things. Example 1, following is the graph of f of x. Use the graph of f of x to sketch the graph of f prime of x, the derivative of f of x. So, what are you given? Well, all you're giving is a graph. This looks like a cubic function. It has 2 turning points. It goes down on the left and up on the right. It increases from negative infinity to negative 4, decreases from negative 4 to, looks like 3, and then increases from 3 to infinity. It is concave down up until somewhere around here, and then changes to concave up. So we have an inflection point somewhere right here around the middle. The first question I'm going to ask is, where is f of x decreasing? And as I noted before, it goes down from x equals negative 4 to x equals 3. Okay, so here is its decreasing interval. Now, the question we're going to ask now is, how does this influence the graph of the derivative? Well, wherever the original graph decreases, f prime is negative. Why is that? Well, remember that the derivative of a graph is the slope of the tangent line. So if our slopes are negative right here, from negative 4 to 3, then the derivative must be negative, right? The derivative is the slope of the tangent line, so the slope of the tangent lines are negative, and the derivative is negative. So for step 2, f prime of x is below the x-axis on the interval negative 4 to 3, because f of x is decreasing there. So that means when we graph our derivative from negative 4 to 3, the entire graph will be below the x-axis. Now this brings up an interesting point. Will the graph of the derivative look like the original? And most likely it actually won't look like it at all, okay? And that's why we're taking this step by step. All we know is the derivative will be below the x-axis from negative 4 to 3. Okay, so it's going to be down here somewhere. Doesn't mean it's going to be decreasing. In fact, the derivative could be increasing from negative 4 to 3, just so long as it's below the x-axis. So make sure you're relating step 1 to step 2. All we're saying is, since the original function is decreasing in step 1, that the derivative graph is going to be below the x-axis from negative 4 to 3. Step 3, we're going to look at where f of x is increasing. So let's take a look. Original graph goes up from negative infinity to negative 4, and from 3 to infinity. So in the same way, since the original graph is increasing, meaning the slopes of the tangent lines are positive, the derivative is going to be positive, or the derivative will be above the x-axis. Step 4, f prime of x is positive on those intervals from negative infinity to negative 4 and 3 to infinity, because f of x is increasing there. So don't confuse the fact that, oh, well, since the original is increasing, the derivative is increasing. No. Since the original is increasing, the derivative is above the x-axis, meaning it's positive, because the slopes of the tangent lines are positive. Step 5, where does f of x have horizontal tangents? Well, we can see it has one right here, and it has one right here. So at negative 4 and at 3. do you think that means for the derivative? Well, if the slope to the tangent lines equals 0, then the derivative equals 0, meaning the derivative is going to cross or touch the x-axis. So for step 6, f prime of x has x-intercepts. F prime of x has x-intercepts at -4 and at 3. Now, I need to change something here. No, that is correct. I'm sorry. -4, 0, and 3, 0, because f of x has horizontal tangents there. So it will have two x-intercepts here because f of x has horizontal tangents. Just think of this, the slope of the tangent line. You know, the slope of the tangent line for the original graph determines what the y value is for the derivative graph. So for example, I mean, just another example. Let's say the slope of this line right here at x equals -7 is, say, 4. Then the point on the derivative graph would be -7, 4. It'd be up here somewhere. So one thing you could do, would be very tedious, is to actually go through every single x value and figure or guess what the slope of the tangent line is, and you'd have a bunch of points, and you could just plot them. So the derivative is all about the slope of the tangent line. Okay. Step 7, where does f of x have vertical tangents or cusps? Well, this one doesn't have any, but just be thinking about what would that mean for the derivative. Well, it would mean that f prime of x has no, it would mean that f prime of x has asymptotes. Now, why is that? Well, a vertical tangent basically means the slope of the tangent line has become infinite, more or less. So you're going to have a vertical, you're going to have an asymptote for the derivative where the tangent line approaches infinity or negative infinity from the left and right. So that means the derivative would approach infinity from the left and right. The same can be true for a cusp. For example, something like this. The tangent lines actually do approach infinity as you get closer and closer. So that means that the derivative graph would approach infinity and therefore it would have an asymptote. But in this case, f prime of x doesn't have any of that because the original graph doesn't have any cusps or vertical tangents, i.e. places where the slope of the tangent line approaches infinity. So remember, it's all about the tangent line. Step 9, where does f of x have sharp edges? This doesn't have any sharp edges. Now what we're talking about is something like this. Well, if it had a sharp edge for the original, then the derivative wouldn't exist because the tangent line doesn't exist. Okay, so f prime of x would have a hole there. F prime of x would have holes, but this time it doesn't because f of x has no sharp edges, i.e. abrupt changes in the tangent line. So if you think about it, you know, like this, like absolute value of x, for example, tangent line goes from -1 to 1. So if you were to graph the derivative, it would look something like this, and you'd have holes there for the derivative. At this point, let's say this would be 0, so you'd have a hole here at -0, -1, and 1 at 0, 1. And that's why the tangent line doesn't exist. Step 11, where is f of x concave down? Well, concave down means the water falls off. So from negative infinity to, we're going to guess, about -0.5, the water we pour on here, upside down u, would fall off. Another way of thinking about it is the slope of the tangent line is decreasing, becoming more and more negative. So this one's kind of tricky. What does this mean for the derivative graph if the original graph is concave down? I'll give you a second to think about that, and then we'll explain that. Well, you can imagine if the slope to the tangent lines are decreasing, and the derivative has to do with the slope of the tangent line, then the derivative will be decreasing. So wherever f of x is concave down, f prime of x will be decreasing because the slope of the tangent lines are decreasing. So f prime of x is decreasing on the interval -infinity, -0.5, because f of x is concave down there, and therefore the slopes of the tangent lines are decreasing. In the same way, we can talk about concave up. Where's f of x concave up? Well, in this case, from -0.5 to infinity, this graph will hold water. The tangent lines are going to increase. Here to be negative, for example, and then over here become more and more positive. So we can imagine that if the original function is concave up on this interval and the slopes of the tangent lines are increasing, then the derivative is increasing since the derivative is the slope of the tangent line. So f prime of x will be increasing here. F prime of x is increasing in the interval negative 0.5 to infinity because f of x is concave up there, and therefore the slope of the tangent lines are increasing. All right. So again, whenever you plug in an x value for the original, whatever the slope of the tangent line is, gives you the y value for the derivative. So if the tangent lines are increasing, then the y values are increasing for the derivative. 15, where does f of x go from concave down to concave up? Well, at negative 0.5, it goes from concave down to concave up. Now we just showed that that means the derivative graph is going from decreasing to increasing wherever it goes from concave down to concave up. So since that happens here at negative 0.5, and since the derivative goes from decreasing to increasing, that means it's a relative minimum. F prime of x will have a relative minimum at x equals negative 0.5 because f of x continuously transitions from concave down to concave up, meaning the slopes of the tangent lines of the original go from decreasing to increasing, concave down to concave up. So there will be a relative minimum there. We also need to mention step 17, where does f of x go from concave up to concave down? You can imagine that if that were to happen, the slopes of the tangent lines would be going from increasing to decreasing. So the derivative would go from increasing to decreasing, and it would be a relative max there. Whenever that happens for step 18, f prime of x would have a relative maximum. This doesn't occur because f of x does not continuously transition from concave up to concave down. Remember, it does have to be continuous, otherwise there won't be a point there. We can get really in depth here. Where does f of x have the steepest negative tangent line? Well, these are all positive tangent lines, so only here does it have negative tangent lines. It looks like at negative 0.5, to me, it's going to be the steepest. So what does that mean? Well, if the original has the steepest negative tangent line right here, that's going to be an absolute minimum for the derivative. Because remember, the derivative is all about the slope of the tangent line, so if that's the smallest or the most negative tangent line slope, then at x equals negative 0.5, they will have an absolute minimum because f of x has its smallest slope of the tangent line here, or most negative you can think of. Now, if you really want to know the actual point, you can measure what the slope of that is, or at least guesstimate. Now, to me, it looks like maybe about -2. I don't know. -1. So the derivative graph would have a point right here. Remember, the y value is all about the slope of this line. So if you wanted to guess, it'd be about -2. We'll get to that in a second when we plot our points. In the same way, where does f of x have the steepest positive tangent line? Would have the graph of the derivative would have an absolute max, because that'd be the steepest slope. So that'd be the highest y value for the derivative. But this keeps on going on and on and on. It's going to get steeper and steeper and steeper. And so for that reason, f prime of x will not have an absolute maximum in this case because the tangent lines increase without bound. Now we get to the plotting our points and asymptotes. Well, right now we just have some x values, so you can estimate the slope of the tangent line to figure out your y value. What points do we have? Well, we have a relative extrema, and we have a few other points, so let's take a look. First, we're going to plot our x-intercepts, and then we're going to go from there. So I'm going to plot points at -4, 0, and 3, 0. Okay, now remember, this is the graph of f prime of x. Okay, so this is a good start, okay? And we can use our increasing, decreasing intervals once we plot our other point. We also have a relative min and an absolute min. So let's see what those were. So at x equals negative 0.5, we figured out it had a relative minimum. But again, we might want to figure out what the slope of the tangent line is here, because then we can get a more accurate y value. So let's take a look. Okay, so what I did was I actually estimated the slope of the tangent line at negative 0.5. I found 2 points on that line and found the slope to be negative 5/2, so negative 2.5. So when I go to graph my derivative, I know that the relative min is going to be somewhere around negative 0.5, negative 2.5. Again, that's just as an estimate, but this y value comes for the slope of the tangent line there. Unfortunately, when we found our absolute minimum, it was actually at exactly the same point. So it will also be the relative minimum at negative 0.5, negative 2.5. So let's go ahead and put one there. Now again, this is just an estimate. And now what? Well, those are the 3 points we figured out. How do we connect these dots? Well, that goes back to increasing and decreasing. It's also going to go back to where the graph of the derivative is going to be above or below the x-axis. So let's review that. Remember, we found that it was going to be above the x-axis from negative infinity to negative 4. So I can safely assume that my graph is going to be up here. Okay. We also found out it's going to be decreasing up until negative 0.5. So I can safely pretty much know that my graph is going to be above the x-axis until negative 4, but it'll continue to decrease until negative 0.5. I also know that it increases from negative 0.5 to infinity, and that it's above the x-axis from 3 to infinity. So it looks to me like it's just going to be a U shape with a minimum right here, at negative 0.5, negative 2.5. Step 24 then is to connect the dots, and this is what it's going to look like as a rough sketch. Everything that I've plotted. And again, does the graph of the derivative look like the original? Well, not really, okay? Now again, just to reiterate, we used decreasing intervals and increasing intervals based on the concavity of the original. We used the fact that it was positive for wherever the original was increasing, so right here, and then negative for wherever the original was decreasing. A little bit. But does it look like the original? Well, not really, okay? Here's what our original graph looked like, and you can see it really looks nothing like the derivative, but that's okay. It's still sound, and we still used calculus to figure out what it looks like. So let's take a more further look, and then we'll be done with this. Okay, I've kind of zoomed here on the graph. We're going to first take a look at the direction, the original, increasing, decreasing, and then increasing, and we can see that the sign of the derivative is going to be above the x-axis, below the x-axis, and then above the x-axis based on where the original is increasing and decreasing. We can see that wherever the graph of the original has extrema, the graph of the derivative will have x-intercepts. We can further see that the concavity of the original determines where the derivative decreases when it's concave down and increases when it's concave up. We can also see that a point of inflection for the original will determine an extrema point for the derivative. And that's it, folks. Again, when you put them on top of each other, they don't look very much alike, but as long as you take it step by step, you can get a very accurate graph of the derivative every time. If you have any other questions about this lesson, let me know.